Welcome back. Still working with motion in a straight line or one dimension. So you can see by the yellow highlighters we've covered quite a bit. Today's green highlighter goal is the acceleration time graph. So by the end of today I'll be able to recognize the correct technique, either read the graph, find the slope, find the area, needed to extract information from a graph. And they could be position time, velocity time, and our new one's going to be acceleration time. So a quick recap. Position time graphs. Okay, so they look at the behavior of an object and its position relative to some reference point. Okay, so objects can move away from or toward. That's in part of our description. And the key piece that we need to walk away with was the rate of change on a position time graph was our velocity. And we talked about there are different ways to find rate of change. We could do it with an average, which is where we take 2 points and we find the slope. And that average is how we represent the velocity over that interval. And we also talked about instantaneous, which is a tangent line drawn at exactly 1 point on the graph. The instantaneous, we would be using tools like rulers and measuring at this point in time until we get to the math skills necessary in future courses. Okay, so the key thing to walk away from there is position time graphs. The rate of change is the velocity. On a velocity time graph, so we plot the velocity values with respect to time, there are two pieces we need to know. The rate of change on a velocity time graph is acceleration, but the area under a velocity time graph is the change in position. So there are two pieces we can find. The slope here would be our acceleration. The area under the graph is our change in position. Okay, so those are the two pieces, and we're going to use all of this today. Our new one is acceleration time graphs. So acceleration time graphs describe the acceleration of an object with respect to time, just like the other two. Okay, so if the graph on the right represents uniform acceleration of an object at 4 meters per second squared. So you can see there, and if you look at the graph, you can see over the entire 5-second interval, the graph is always at 4 meters per second squared. For this level, of course, your acceleration will always be constant. We won't have changing accelerations unless we break the problem up into smaller chunks. But for us, our acceleration time graphs will be pretty basic. So the key here is the area under the graph represents the change in velocity. Okay, so in this case, there is no slope value that we're worried about. For acceleration time graph, we're only interested in the area under the curve. So if we were to look at this for the change in velocity for the first 5 seconds, okay, if we found the area underneath this rectangle right here, we would have 4 meters per second squared times 5 seconds, and that would give me 20 meters per second. So you'll notice that the area with the units included, when you multiply those values together, we get a velocity. Okay? Now that velocity isn't the actual velocity of the object, it's just what it's changed at. So if it started at 0, it's gone up to 20. If it started at 20, it's gone up to 40. Okay, and we can't extract that information without a little bit more detail from the questions. So all we know that this is the change in velocity. That's a really important piece to understand from these. So for our course, we'll only have constant acceleration. There will be no variable accelerations in this course. So it'll either be constant or none. Just those are the two options for us at this point in time. So let's do one. So if we take that same question, we're traveling at 4 meters per second squared. That's our acceleration. If we find the area of that red line, that would be 0. If we go to 1 second and we find the area here, okay, you'd have 1 times 4. That's a change in 4. And what I've done is I've organized that information into a table. If you go to 2 seconds, the total area under that graph would be 2 times 4, or 8. And these are giving me my changes in velocities. Okay, so we're going to make sure or assume we start at 0. So we're going to assume V initial, the starting value was 0 meters per second, just to make this a little easier for our next step. So I generate this table here of all of my change in velocities just by finding the areas under the acceleration time curve, or time graph. If I take those values and I put them in a nice little table, so I've just basically taken all of this information and plotted it into this little table. Okay, and then I set up a graph to plot those velocities. And again, we're assuming we started at 0. I have a new graph that is my velocity time graph. So you'll notice the areas under the acceleration time graph, the AT graph, lead to my velocities. Now, if I find the area under my velocity time graph, I will find positions, or change in positions, my displacements. So here's the velocities. I just reproduced it again so it's all on one page. If we go in here and we find the area at that location, it would be 0. If I find the area here of the first triangle, okay, so that would be 4 times 1 divided by 2. Okay, and I've done all of those calculations right here for you. We would generate a new position time table. Okay, and then we can plot those points. Okay, and if we take all of these points here that are generated from finding the areas under the VT graph, and then we plot them over here, we get, no big surprise here, we get the curved graph of non-uniform motion that we've already previously discussed. So here is our curve of accelerated motion, and we've developed it straight from our acceleration time graph. Okay, and if you wanted to do a little check again, we talked about tangents. If you draw little tangents at all of these dots, you can see they're progressively getting steeper, which means the rate of change of our position time graph, which is velocities, is increasing, which means we have accelerated motion, which we knew from the start of the problem. Okay, so let's just sort of take a look at this big picture. You don't need to know where this comes from, it's just provided. But what I would like you to see, okay, here's the graph. This is just a quadratic that you would see in grade 10 math. Okay, you can see it's a sad curve. There's a leading negative out front. We've generated the values, plotted the graph. A couple of interesting locations though. If you looked at all of the little instantaneous or tangents here, all of these here have slopes that are positive. And if we put some fictitious values on them, say you went to 100, 50, 20, 10, 5, you'd see they're all positive numbers, but they're getting smaller. Lastly, at the very top, where the rocket has stopped for a second, you will see that m equals 0. And that's just a brief instant. If you drew a couple more tangents on this side, the number of values don't really matter so much as maybe this is -5, -10, -30. You can see all of those are negative now, and they're increasing in magnitude. So when you plot those, if you were to, you would see them all along this line. The key one being this 0 right here. So you can see that location where the slope is 0 of the instantaneous velocity right at the top also plots at 0 on our velocity time graph. All of these guys are positive. They plot in the positive realm. All of these are negative. They plot over here in the negative realm. Okay? Now, if we were to find the slope of this velocity time graph, we would find that it is constant because it's a linear relationship you can see here. We would actually find it's -9.8. And then we could plot that down on our acceleration time graph right here. Okay, and now what we really want to investigate or explore here is to move from one graph to the other. To move from a position time graph to a velocity time graph, we do that via rate of change or slope. To move from a velocity time graph to an acceleration time graph, we move via rate of change or slope. So to move down, we're using rate of change. If we want to move up, so if we want to move from an AT graph, acceleration graph, back to a velocity, now we're using areas. to move from a velocity time graph to a position time graph, now we're using areas. Okay, so that's how we move amongst the graphs. There are some interesting connections. This one here was a second degree problem, the second degree implying that exponent is a 2. When we move down a graph, it switched to a first degree. The t value has an exponent of 1. And then we move to a constant, which would actually have a t value of 0, but we don't typically write that because that's equal to 1. So you'll notice that the degree or the power of the variables is changing as we move through graphs. Okay, so let's just explore one that's a little bit more complicated. Again, you don't need to know where this guy comes from. What we do need to see is that if we multiplied all these out, we would have some t cubed somewhere in the final expression. If we look at this graph here, which is a cubic, we'll see we have positive slopes on that side, we have a 0 slope at top, and then we have negative slopes on the right-hand side. And they continue all the way down here until we go back to a 0, and then we go back to positive slopes. And again, I don't really care about the numbers at this point. I'm just interested in the behavior. So if I plot positive slopes going towards a 0, whatever the numbers might be, they would do something like that. So that's positive values heading towards a 0. On this in-between or middle interval, I have all negative value slopes, and they have to go from 0 into negative numbers back to 0. And lo and behold, it would do something like that. And then lastly, I have positive slopes again. They would plot in the positive section. So now if we look, maybe I'll change the view here. We can see things that align. This is a 0 slope, it plots at 0. This is a 0 slope, it plots at 0. And now if I look at a cubic, which is the top one, a third degree problem, when I move down one graph, it turned into a second degree problem. Okay, so now if we look at our second degree problem here, which is our velocity time graph, okay, I would have positive slopes plotting on this side. Negative slopes. On this side, I would have positive slopes, and at the very bottom, I would have a slope of 0. Okay, so if I come down and I plot 0 here, and now I plot negative slopes on this side, moving toward positive slopes. I don't know what the values are. I'm not going to calculate them right now. All I'm interested in is the behavior. So if we take a look, third degree, move down a graph, went to second degree, move down a graph, I'm at first degree. And if you were really ambitious and we could follow what the rate of change of acceleration is, you could actually go another graph and you'd end up with a constant value. Okay, now this is a precursor to calculus. I just want you to see how some of these connections are made. You don't always have to have numbers to be able to follow the concepts. What we're interested in is how we move between the graphs. So rates of change move us down, areas move us up the series of graphs. Okay, so on page 35, numbers 1 to 4, there's a couple to try. Thanks for tuning in.